example here, I just make one. Okay, so here the sigma x equal to 10, and for example sigma y compressive equal to 2, and here for example analytic equal to 5. Okay. So the way we draw the Mohr circles is this. We simply look at this. This is a 3D stress element. And in each viewpoint, from the viewpoint in each direction, we see in front of us will be, projection to us will be plane. So here is this. If you imagine you are the small guy, for example, sitting in x-axis, looking into this element. So that means once you're looking into this element in front of you, is this. In front of you, you see this is y-axis and this is z-axis only, because you are in the x direction. So in front of you, you wouldn't see the 10. So that means the distribution of the stress is here, 2 and 5. So with this one, we can draw the Mohr circles quickly. So for this case, the Mohr circle will be, let me draw here. One is 5 here, one is minus 2 here. Let me draw it bigger. I need a bigger one, sorry. Here is 5, here is minus 2. Okay, so this Mohr circle corresponding to is this viewpoint because there's a no shear stress. Okay, so this Mohr circle is in terms of in the x direction, looking into in the x direction. So why not here the Mohr circle? Let me call this is x. Okay, so the Mohr circle, let me label it. So this is the circle corresponding to we're looking to in the x direction. And now we change our viewpoint. So for example, we change to say sitting in the y-axis and then looking to that one. So the second viewpoint in front of us is this. Again, looking into the direction in the same way, in the way we designate. So here is the z-axis, and here is x-axis. And at this moment, don't care about the right-hand rule. We just draw whatever we see. Okay, so x-axis will be in this, z will be here. So in the z direction, we have the normal stress tensile 5. In the x direction, we have 10. So here you can see the normal stress. This is the principal stress. One is 5, minimum, maximum at 10. So here, let me enlarge here. So 10 is here. So corresponding to that circle is this. Okay, there should be tangent here. So for this one, this is looking in the y direction. So here we label as y. So here we just label this circle corresponding is looking into in the y direction. Okay, and they shouldn't be equal in size, but my drawing is not so perfect. This one has a radius 2.5. This one has a radius 3.5. So this circle should be a little bit bigger than this one. Okay. Then finally, we're looking into the viewpoint sitting in the z-axis looking down. Okay. So if we sit in the z-axis looking down, then what we're seeing is the x-axis and y-axis. So here, for example, we're looking down, say this is y-axis, and this is x-axis. So in the x-axis, we have 10 normal stress. In y, we have 2 here. So that circle corresponding will be this bigger one. Okay. So here is -2, here is 10, so that is a circle like corresponding to this. So again, the circle, the biggest circle tangent at here. So this corresponding is a viewpoint in the z direction. Okay, this label as the. So from here, we simply apply is this. We look into this 3D principal direction, and in front of us is the simple, a projected two-dimensional the distribution of the principal stresses. So for each one, we can easily draw the circles. And so in here, we use 3 more circles to represent these 3D dimensional elements. And using these circles, we can quickly answer the question is this. Let me ask you, what is the maximum stress? What is the maximum principal stress? What is the maximum normal stress for this case, for this example? 10. And what is the minimum principal stress? That's -2. And what is the maximum shear stress?
Here?
That's 0. What is the maximum shear
the
stress?
radius of the
Radius
right?
of the circles. Right now we have 3 circles, and I'm looking for the maximum one. So that should be this one, biggest one. The biggest one, the circle has a radius 6. So for this case, the maximum will be equal to 6. Okay, and the maximum happened in which orientation? The maximum corresponding is in this circle. So let me label it. Okay. So that means here is the maximum. I just try to overlap here. So here, maximum occurred is in this orientation, right? So here from this orientation, I want to even to tell you in which cross section the maximum shear stress occurs. This is this graph, this viewpoint, this distribution of this stress element corresponding is this biggest Mohr circle, and this is a given viewpoint, and we want to we know that for in terms of this one, the maximum is happen to here. So for example, you can see this plane has the coordinate is 10 and 0. So this corresponding to is the x point on this viewpoint. In the y plane, we have the coordinate -2 and 0. So this point corresponding to is this point. So now you can see the maximum occurred here. So either we can rotate, for example, here on the Mohr circle, say go to either counterclockwise directions, or we go to clockwise direction either way. So for example, say let me choose is go to these directions. Okay, so here from here if I would choose go this direction, that is 90 degrees. So that corresponding to is we rotate this element by 45 degrees. In this orientation, we would able to see the maximum shear stress equal to 6. Okay? And then from here, for example, if we choose counterclockwise, then we choose to rotate this diameter in this way. So this is x prime. So the x prime has the coordinate equal to how much? The diameter is 6. So here, this coordinate here should be 4, and this is 6. And 6 is in this way. So we label this carefully. So for example, here we rotate in this orientation, then x prime will be here, the y prime will be to here. And then we can label x has 4, and 6, that's the shear stress, point upward or downward. I'm waiting. Look at this one. So that should be here, right? So this symbol meaning is this. This shear stress on the side would have a tendency to rotate this stress cube in the sense of this direction. So that is 6 here. Okay. So, yes.
Did you change your orientation on the, so for the viewing it from Z, you rotate it 45? It looks
Yeah,
like
so for example here, like this longer side is x-axis. Okay, so right now we rotate 45 degrees. So x-axis will be going that direction, right? Right now x-axis is here. So go to 45.
I think your axis on
Yeah,
the...
you're
Oh, so x-axis will be which way? Here.
I thought it was just the Y. Should that
Yeah,
Y
that's-
be the other way?
So
yeah, something was off.
so that should be, this should be x, right? Sorry, this should be y.
Okay, yeah.
So let me change it. That is good. Good catch. So here should be 6, and here should be, this is 6, and this is 4. Good.
I got a question.
Yes.
So you know how you've got your 3 boxes right there with each plane?
Hmm?
On the Z direction, that's like I'm looking down onto the box.
Okay.
And so if I'm looking down at the box with the
Looking down in the box. Okay, so that means since in this way, looking down the box, let me draw it this way. So looking down the box, in terms of that one, we should be like this. So here should be x, this should be y, right?
That's what I'm getting at.
Yeah.
And that's, isn't that opposite or does it matter?
It matters. So would you able to modify your things like this? So in terms of this way, so let me go in this way. So this will be x and y, right? Okay,
Yeah.
so in this way, this will be, x will be 10, and this will be 2. So then again, okay, this one, I try to fix the directions. So this circle is still corresponding to this one. So now we rotate 45 degrees. So 45 degrees, then that will be x prime and y prime like this. Okay, so let me fix this one. So in x prime we have 4, so normal stress is 4, and 6 is in the same. So right now, which is the direction of the stream? Going up or going down? Right now, this point?
Is it down the way you have it rotated? Or is that
This
just
is the sense, this meaning is the sense of the string to rotate the stress element
so it's
around
going
the
up.
region. So it should be going up, right?
Yeah.
Okay, so this is 6. So would you modify this one into this? So those are the 2D planes, and in actually, you can see this one is to rotate about z-axis by 45 degrees. I want to draw this orientation in this block. So that one, again, this is the orientation happened by rotating this element about z-axis by 45 degrees. I rotate this about z-axis by 45 degrees. So that is the orientation here. That is the, again, you look at this cube, and we rotate about z-axis by 45 degrees. In that specific orientation, that will be a line cube, what I'm going to draw here, this green plane. This is the diagonal plane that is in the orientation we talk about. We're rotating this one about z by 45 degrees. So in the orientation parallel to the green one, we would see, we can measure, if we will be able to measure, we will be able to measure the maximum shear stress will be equal to 6. That will be in this orientation drawing here. And that can be tell is this, because here, the 45 degrees we identify is corresponding to the biggest circle. The biggest circle is about this viewpoint. And how much? Rotating on the Mohr circle by 90 degrees, that means about the z-axis by 45 degrees. So that means we're back to here, we work on the original, then that should be in this spring plane. Is that okay? Okay, that should be a little bit more straightforward. So that is the applications of the principle, the stresses for three-dimensional case. And again, for three-dimensional stress element, we always expect for three circles. And the three circles must be tangent to one another. If your drawing couldn't find any tangent things, then that indicates you have the calculation mistakes there. Okay, the three circles must be tangent to one another. So that is the topic, and textbook has more illustrations for this kind of the plane for 3D. So probably you can get more information from the textbook. And so the very last topic I want to give to you is application. We call it pressure vessel. So pressure vessel is a very simple and straightforward the application of the Mohr circle. The formulation is very straightforward. So here I directly do the PowerPoint slides. What is a pressure vessel? If you go first mile to buy propane tank, and that usually come with, it should be the cylindrical shape. Okay, and from there basically they sell by pounds. They have the gas being compressed there. They sell by pounds, I think. And gas is kind of heavy, right? So usually you buy is a smaller one. I don't know how much that one, 20 pounds? I think the price they charge is per pound. And there's even the larger tank. I think that's a 3 foot tall. And there the propane gas has been compressed in that tank and for use. And so that could be the one very ready application for this case. And so for the pressure vessels, we like to know is, given the size and the thickness of the vessel, we want to calculate what would be the stress that imposed by the internal pressure to the sheet of the tank. And the one here, if you wish, you can, in your notes, you can write it up, is one assumption is here we assume the thickness is small, comparatively small compared to the diameter or compared to the length. And how small that could be, we say 1 order of the magnitude smaller than other dimensions. If the tank thickness is too thick, then the theory we're going to displace here won't apply. Then we'll have to apply the other theory we call the thick wall theory. And that will come up with the nonlinear expression. So here we just simply assume the thickness T is small, okay? So under these situations, then for the stress on for the stress in the thickness, we can assume pretty much is uniform. So here we assume the thickness is small, so that means we can assume the distribution of the stress at the interior surface and or anywhere inside the wall or at the outer surface, everywhere, that should be the same. That wouldn't have a big deviations. If the thickness is too thick, then the distribution of the stress wouldn't be uniform, wouldn't be constant. So here we simply take out the simplest version for this one. Okay, so here we can take about is this. For example, here we assuming sigma 1 is we call the hoop stress. Sigma 2 is called the longitudinal stress. And on the cheat sheet, I only provide you the equation is in terms of sigma 1 and sigma 2. and I didn't tell which one is which one. Sometimes I would myself, I would forget which one